Universal gravitation. In this lesson, we're talking about gravity in space, the law of universal gravitation, the power of gravity, how gravity affects the tides, objects in circular orbit, and our bodies in microgravity. Gravity in space. So what I'd like you to do is pause the video and answer these 4 questions to the best of your ability. Number 1, is there gravity in space? How do you know? Number 2, what do astronauts experience? And that's in regards to gravity. Number 3, why do they experience it? And number 4, what are its long-term consequences? So that would be the long-term consequences of your answer in number 2. So again, I'd like you to pause the video, answer these 4 questions, and we're going to come back to them later in the lesson. Gravity is everywhere. Gravity is present wherever there is matter. Matter is anything that's composed of particles and takes up space. Thus, all material things are exerting a force on all other material things. That includes the person beside you, your desk, the pencil you're holding, the roof over your head. All these things are made of matter, and they're exerting a gravitational attraction force on you, and you're exerting a gravitational attraction force on them. The formula to find gravity is this one right here. Big G, M, which is going to be our mass 1, so that could be you. Mass 2, which in this example could be the pencil. And then R, which is the distance between the center to center. And this is the law of universal gravitation. So Fg, as we just talked about, was the force of gravity between any 2 objects. So that's the force of gravity. G is the universal gravitational constant, and it's this really small number here. You'll notice it's times 10 to the negative 11. The force of gravity is very weak. The only time that it makes an impact is when the objects that are involved are really large. And 1 and M2 are the masses of the objects in kilograms, and R is the distance separating the 2 objects center to center. So again, we're not talking about here to here. We're talking about center to center, and that gives us our R value. And you'll notice that R value is squared, so it's going to be the inverse square rule. So this 1 over R squared. So what does this mean? Well, this is the inverse square rule. With each increment, the space covered by the light is increased by the square of the multiple. So you can see on the first increment, we cover 1 box here. On the second increment, we have 4 boxes. And on the last, we're going to have 9. Because this is going to be 3 squared, this is 2 squared, and this is 1 squared. So you can see as we double the distance, we get 4 times as much coverage. As we triple the distance, we get 9 times the coverage. That means we can just spread that light, or in this case gravity, like we were talking about previously, into 9 different equal sections instead of the 1 that it came from. So as we get away from the source, the force in this case becomes smaller and smaller and smaller. Now, as we did say, gravity is everywhere. Gravity acts between any 2 objects, equal forces acting in opposite directions. So if you have the Earth and the Moon, even though the Earth is much bigger, and as a result the Moon orbits the Earth, we get the same attraction between the Earth and the Moon as we do between the Moon and the Earth. The masses must be large to notice a G-force. So if you have 2 people, that G-force between them is going to be really small. If you have a person and a pencil, that G-force is even smaller because the masses are really tiny. But if you have 2 planetary bodies, the masses are so large that you can notice a force of gravity. As we get further apart, the force of gravity becomes smaller and smaller and smaller. And this is based on our 1 over R squared value that we talked about previously. And in space, we experience very little gravity due to increased distance from any large mass. This is called microgravity. The power of G. The gravitational attraction between the Earth and the Moon and the Earth and the Sun is responsible for the high and low tides. And you can see examples in this picture. And you can see 3 examples here. All these boats were once in the water, and you can see where they are in these 3 pictures. Right there, there, and there. What we'd like you to do is pause the video and watch number 2. It's a really great look at these high and low tides. The power of G. So which has a greater effect on Earth's tides, the Moon or the Sun? Why do you think that is? What I'd like you to do is pause the video, answer those 2 questions, and then watch number 3 to find the answer. The power of G. So now that you've watched the video, which has a greater effect on Earth's tides, the Moon or the Sun? So although the Sun is much larger, has a much larger M value, which we're going to see in this part right there, it is much, much further away. So this R value becomes really, really big, but at the same time, we're going to square that multiple. The Moon's closeness significantly outweighs the Sun's huge mass according to the law of universal gravitation. And again, we can see that because the masses are only a multiple of 1, whereas the R values are squared values. So in terms of gravity, distance plays a much larger role than mass. Spring and neap tides. When the Moon, Sun, and Earth are in line, the gravitational pull is added. This is called a spring tide, and you can see that in our first example right here. So you can see we have the Earth, we have the Moon, and we have the Sun all lined up together in a straight line, and therefore you get a pull equal. Now you can see there's going to be a bulge here, that's going to be a high tide, and you're going to have a bulge over here, that's going to be another high tide. Now that doesn't matter whether the Moon is on the right-hand side or on the left-hand side. As long as the Moon, Earth, and Sun are all lined up together, you're going to get a bulge at both sides. And this is because the water is being pulled towards the Sun, but also the Earth is being pulled to the right a little bit, giving that extra space on the left-hand side here. When the Moon and Sun are at right angles to each other, the effects partially cancel out. So you're going to get the pull of the Moon, getting this bulge up here, but then you're going to get the pull of the Sun, reducing the bulge and actually making a tiny bulge over here. So what happens is that we still get a high tide over here, but it's a smaller high tide than the high tide that we see in spring tide. And then when the Moon is at every other part in the cycle, so here, 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 we get variations of these tides. Extraterrestrial gravity. Extraterrestrial gravity is gravitational acceleration on other planets and stars and can be calculated using this law as long as the mass of the planet is known. Now gravity is dependent on both radius and mass of the object. So you can see that any object that has a radius and a mass similar to Earth, so Earth is right here, so an example of that would be Venus. Venus's mass and radius are very similar to Earth, are going to have a very similar G value. You can see 9.8 versus 8.83. But then you have a planet that's smaller, so say Mars. Mars' radius is about half, and its mass is significantly less as well. And it's going to have a significantly lower G value, 3.75 versus 9.81. And then if you look at a planet that's much larger, say Jupiter, with a radius that's about 10 times that of Earth, but a mass that is significantly higher, 1.9 times 10 to the 27 versus 5.97 times 10 to the 24. And its G value is 26, which is a significant increase over Earth's 9.81. So the larger the planet, the larger the G value. Check your understanding. Earth's gravitational pull on a spacecraft some distance away is 1.2 times 10 to the 2 newtons in magnitude. What will the magnitude of the force of gravity be on the second spacecraft with 1.5 times the mass of the first spacecraft at a distance from Earth's center that is 0.5 times as great? So let's write down what we have. We have Fg, we know is 120 newtons, and what we're changing is the mass. So we're going to say m1 is going to change by a factor of 1.5, and the distance, or the r value, is going to change by 0.45. Now the only values we're concerned with are the mass, radius, and Fg. So we can set up that ratio and then make it a multiple of the Fg we currently have. So we're going to say 120, and then we're going to multiply it by 1.5, because our mass 1 here is a 1.5 multiple, and then we're going to divide it by our change in r, which was 0.45, and then don't forget to square the value like that. So what you're left with is 120 times 1.5 divided by 0.45 squared. And that gives you an answer of 8.9 times 10 to the 2 newtons. Now there's no direction in this because it's between the two objects, so depending on your perspective, it would either be towards one or towards the other. Check your understanding. Determine the magnitude of the force of attraction between two uniform metal objects of mass 4 kilograms. The centers are separated by 45 centimeters. So like to pause the video and answer this question. So we're looking for Fg, that's our question. We're told that mass 1 equals mass 2, which equals 4 kilograms. And we're told that the r value between them is 45 centimeters, which equals 0.45 meters. So we get Fg equals to our g value, which is 6.67 times 10 to the negative 11, times mass 1 times mass 2, divided by 0.45 squared. And that gives us an Fg value of 5.27 times 10 to the negative 9. Objects in circular orbit. An object in circular orbit like a satellite has a forward motion, but is constantly being pulled by the force of gravity towards Earth. If the orbiting object maintains its forward motion without changing its distance from Earth, it will continue to fall around Earth in a circular orbit. So you can see it's got a forward motion to the left, as shown right here, but it's also got a force of gravity coming down towards the planet. So what that means is still being pulled down, but by the time it gets down, it's already moved forward, or in this case left. So by the time it gets to where the center of the Earth would be, it's over here. And then it's getting pulled again that way, while still having a forward motion of this way, which is larger than its force of gravity. So again, once it would get to where the center of the Earth is, it's all the way over here on the bottom. And then similar, it's got motion towards the center of Earth and to the right. By the time it gets to the center of Earth, it's already here on the right-hand side. So that's why we say that anything orbiting another object is continually missing that similar object. Microgravity. There is gravity everywhere. Microgravity is the condition in which people or objects appear to be weightless. Micro means very small. So is the force of gravity stronger on the moon or the ISS? So what I'd like you to do is first answer the question to the best of your ability and then look it up. So which one has a higher force of gravity, the moon or the ISS? Considering people walk on the moon and float around in the ISS. So is the force of gravity stronger on the moon or the ISS? The force of gravity is much stronger on the ISS compared to the moon. The gravity on the ISS is approximately 90% as strong as on Earth's surface. Objects appear to float because they're in a constant state of free fall. So if you are inside the ISS, and we just talked about on the previous slide how if you are in a circular orbit around an object, you're continually falling towards that object. Well, you are falling towards that object, Earth, and so is the International Space Station. Now, since you're both falling at exactly the same rate, it's like the amusement park rides where the seat drops from underneath you. There's no force acting up, so you feel like you are free falling. And that's the same thing on the ISS. You are free falling, but so is the ISS towards Earth. Since you're both falling at exactly the same rate, it appears as though you are weightless, even though the force of gravity is very strong on the ISS. On the moon, there is still a force of gravity. People can walk on the moon, but you can see how they're always bouncing. The reason that they're bouncing is because the force of gravity is less on the moon. In fact, it's only about 17% of Earth's gravity. Now, how does being in microgravity affect our bodies? Well, the absence of forces against our muscles caused by microgravity has significant long-term health consequences. If you think on Earth, you're always being pulled down at 9.8 meters per second squared towards the center of the Earth. But when you're in space, floating around, there's no pull of gravity. So since there's no pull of gravity, there's no opposing forces acting on your muscles. Since there's no opposing forces acting on your muscles, and there's nothing keeping the fluid balanced the way it typically is, things start to go badly. You get muscle atrophy, which means your muscles start to break down so the body can use those nutrients for other things. Since the muscles don't need to be used, they don't need to be there. Loss of bone calcium, same thing. If your bones aren't needed to keep you up, the body can break the bones down and use those minerals for other purposes. And then you get things like organ swelling. So heart, kidneys, eyes, these things are all going to start swelling because you're going to get a fluid shift inside your body. So how then can we potentially go to other planets? Right now we're thinking about going to Mars, but how could we go further? Well, currently astronauts have a rigorous exercise regime to limit these effects. If you can be strapped down to the treadmill, then you can exercise using it. Any interplanetary mission to Mars or beyond, or permanent space colony, is going to need to stimulate the effects of gravity for the health and safety of the participants on board. And this can be done using the principles of circular motion and center-seeking force. So we think of what that means is that if you have an object rotating around something, so here's its axis of rotation right here in this middle circle thing. So this ball is going down and it's following this path all the way around the dotted line. As it does this, what's happening is that there's a center-seeking force, this centripetal force that you can see right there, that's pulling it towards the center. So it's actually being pulled towards the center as it's rotating around its axis. Now, since there's a force going towards the center, there needs to be an equal and opposite force going the other way. And that's going to be called our centrifugal force. And that's going to be responsible for many things that we potentially have seen in real life. If you go to an amusement park ride and you go on that ride that spins really, really quickly, you get forced to the outside wall, and it's really hard to move your arms. Another example is if you put water into a bucket and then spin it over your head using a string, you're going to be able to keep that water inside that bucket. It can be upside down, but that water is not going to come out. And that's based on this force that's going back out in our diagram on the bottom here. It's the one going to the left. And that one's going to be the centrifugal force, as I was saying. Now, how this could work is if we have a circular spacecraft with a hole in the middle. This is going to be called a torus. And what this torus is going to allow us to do is we can spin it. And as we spin it, we're going to create the centrifugal force against the outside walls. And if those outside walls were the things that we were standing on, we could create a force down on our legs. And therefore, down would be everywhere where we have an outside wall. And we could simulate gravity in all these places. So this would be down, this would be down, that would be down. And as a result, you get an opposing force up, up, up by the floor, which would give us a feeling of gravity and could potentially counteract all these negative effects of being in a microgravity environment for a long period of time. Now, for this to work, we need to have a really big spaceship. That's going to be really key. The bigger it is, the slower the rotation. And we need that. We don't want to have a ship that's spinning really, really quickly, because then we're going to get other effects. We're going to get more gravity on the feet than on the head, and that's going to have other problems as well. So what we need is a really big ship that's going to spin really slowly. If we have these two things in place, we can potentially simulate enough gravity to counteract these negative effects. So let's go back to the questions that we started with. Number one, is there gravity in space? Yes. How do you know? There's gravity everywhere. Anywhere where there's mass, there's gravity. Therefore, there's gravity in space. Another way that we know is that we're going to have planets orbiting other objects. Since we see these orbits, we know that there must be some kind of gravitational force causing these orbits to occur. What do astronauts experience? They experience microgravity, which is the appearance of a lack of gravity when there actually is a gravity around them. And why do they experience it? Because of free fall. If you're inside the ISS, and both you and the ISS are falling at exactly the same rate at exactly the same time, you're not going to have any forces acting up against you, and that's going to be the appearance of free fall and a lack of gravity. What are its long-term health consequences? Well, there's things like fluid shift, bone decalcification, muscle atrophy, among others. It is a significant problem that needs to be overcome in order for us to undergo long-term space travels. And that concludes our lesson on universal gravitation.